Linear systems. A linear system is a collection of one or more linear equations involving the same variables. Let's look at some examples. Here we have a linear system of two equations in two variables. The variables here are x and y. Here's an example of a linear system consisting of three equations and two variables again, the two variables being x and y. This one is a linear system of three equations in the three variables x, y, and z. This one is also a linear system of three equations in three variables. This time the variables are x1, x2, and x3. Here we have a linear system of two equations in the six variables x, y, z, w, u, and v. This one is a linear system of three equations in the four variables x1, x2, x3, and x4. One more example. Here we have a linear system of four equations in the four variables x, y, z, and w. A solution to the linear system is a sequence S1, S2 through Sn that satisfies each equation in the system. Let's look at some examples. 3x1 minus x2 plus x3 equals 4, x1 minus 2x2 equals 1. This is a linear system of two equations in three variables. Is 1, 0, 1 a solution to this linear system? To see if this is a solution to the system, we have to check if it's a solution to each of the two equations in the system. Let's check the first equation first. 3 times 1 minus 0 plus 1 is 3 plus 1, which is 4. Since the left and right hand sides of the first equation do match up when we replace x1 by 1, x2 by 0, and x3 by 1, we see that 1, 0, 1 is a solution to the first equation in the system. Let's check the second equation. 1 minus 2 times 0 is 1, and that does match up with the right hand side. So 1, 0, 1 is also a solution to the second equation in the system. Therefore, 1, 0, 1 is a solution to the linear system. Let's look at another point. Is 1, 2, 3 a solution to this linear system? Once again, let's check the first equation. 3 times 1 minus 2 plus 3 is 3 minus 2 plus 3, which is 4, so that works. And we see that 1, 2, 3 is a solution to the first equation. Let's check the second equation. 1 minus 2 times 2 is 1 minus 4, which is negative 3. This is not equal to 1. So 1, 2, 3 is not a solution to the second equation in the system, and therefore it is not a solution to the linear system. The set of all possible solutions of a linear system is called the solution set of the linear system. Let's look at some simple examples. X plus y equals 2. Y equals 3. This is a linear system of two equations with two variables. We can solve this one pretty easily using the substitution method. The second equation gives us that y equals 3, so we can replace y by 3 in the first equation to get x plus 3 equals 2. Subtracting 3 from each side of this equation gives us that x equals 2 minus 3, or negative 1. So negative 1, 3 is the only solution of this linear system. The solution set is therefore the set consisting of the point negative 1, 3. This system of equations has a unique solution, or exactly one solution. Let's look at this graphically. Let's sketch the graph of these two equations, starting with the first equation. A nice, easy way to sketch the graph of a linear equation is to plot the two intercepts. Let's start with the y-intercept. We'll set x equal to 0 so that we get 0 plus y equals 2, or equivalently y equals 2. So the point 0, 2 is on the graph of the first equation. Let's also find the x-intercept by setting y equal to 0. So we get x plus 0 equals 2, or x equals 2, so that the point 2, 0 is also on the graph of the first equation. Once we have 2 points on a line, that determines the line, and we can draw it. So we have a graph of the equation x plus y equal to 2. The second equation, y equals 3, has a graph that is a horizontal line where the y-coordinate is always equal to 3. We see that these two lines intersect at the point -1, 3. And as you can see graphically, we also have that -1, 3 is the only solution to the linear system. Let's look at another example. X plus y equals 2, x plus y equals 3. If x plus y is equal to both of these numbers, then those two numbers would have to be equal to each other, and that is clearly a contradiction. So the solution set of this system of equations is the empty set. In other words, the linear system has no solution. Let's look at this graphically as well. We already graphed the first equation in the last problem. Looks like this, x plus y equals 2. And x plus y equals 3, if we could graph it in a similar way, we see that the two intercepts are 0, 3, and 3, 0. And when we graph it, notice that the two lines are parallel. They have no points of intersection. So graphically, we could also see that this system of equations has no solution. One more example. X plus y equals 2, 2x plus 2y equals 4. The second equation here is a scalar multiple of the first equation. If we multiply each term of the first equation by 2, we get the second equation. It follows that the linear system has the same solutions as just the single equation x plus y equals 2. So the solution set is the set consisting of points of the form x, 2 minus x, where x is a real number. To see that the y-coordinates of the points are always 2 minus x, we could simply subtract x from each side of this equation to get y equals 2 minus x. So for example, if x is equal to 3, it follows that y is equal to 2 minus 3, or -1. So 3, -1 is a solution to this linear system. There are lots of other solutions as well. For example, 5, -3, because 2 minus 5 is -3. -7, 9, because 2 minus -7 is 9. And as one more example, 0.3, 1.7, because 2 minus 0.3 is 1.7. This linear system has infinitely many solutions. Graphically, as before, we have the graph of the line x plus y equals 2 here, and the graph of 2x plus 2y equals 4 is exactly the same line. So any point on that line is a solution to this system of equations. To summarize, a linear system can have exactly one solution, no solution, or infinitely many solutions. In the past 3 examples, we saw exactly one solution. In the second example, we saw no solution. And in the third example, we saw infinitely many solutions. The first example is a system of equations that is consistent because it has a solution. The second example is of an inconsistent linear system because it has no solution. And the third example is also of a consistent linear system because it has solutions.